where the problem occurs.
What?
All the way back to colligative properties. Colligative properties said number of particles that are released. Nothing about their identification, just the number of particles. If we take sugar, which is not the strong electron we've looked at so far, sugar in the solid phase becomes sugar in the aqueous phase, becomes solvated, but it stays a single particle. When we talk about ionic compounds, now we have a bit of an issue. Now we have, say, something like sodium chloride. Put sodium chloride in water. You get two species out, not one. If colligative properties are based on just the number of particles released, an electrolyte like sodium chloride will produce a greater effect because you're getting two particles instead of one. That can be magnified. Magnesium chloride this gives a total of 3 particles. 1 magnesium, 2 chlorine. Even greater effect should be felt. Gentleman who did the fundamental work on this, a guy named Van Hoff, he came up with the Van Hoff factor. Factor given an I designation. Van Hoff factor mathematically. There's the moles of particles in solution divided by moles of formula units dissolved. In the case of sodium chloride, the Van Hoff factor. Number of particles released in solution is 2. Number of the initial starting unit, number of sodium chlorides is 1. The Van Hoff factor for sodium chloride is 2. We do the same thing for the magnesium chloride. It's 3 to 1. So really the Van Hoff factor is just a mathematical representation of how much gets loose, how many does it produce. When you look at the Van Hoff factor, one thing to remember is that this assumes ideal behavior, that everything just does exactly what we predicted will do. That all of them break, all of them are released, everything is as it should be. You'll see, and we'll talk about it just probably after the break, is that in reality, it may not be exactly 2, it may not be exactly 3. Sometimes when they're in solution, these ions tend to stick together amongst each other, and it lowers the ideal. The Van Hoff factor you calculate from that is the ideal version, when it should be. But in reality, sometimes you'll find them to be a little less. You won't find them generally more, you'll find them to be less. So instead of, say, 3 for magnesium chloride, you may see 2.8. Doesn't mean that 2.8 are being released. It means that sometimes when these ions, positive, negatives, are released, and they stick to the water, every once in a while the whole thing sticks together. You get less ions floating available at any given moment. That's what happens, why it's not always exactly as it should be. If we look now, last thing before we go to break, our laws that we looked at, delta TF now becomes, that's where we put the Van Hoff factor in. What I recommend is when you do the problems, I just use these equations. I use them with the Van Hoff factors. If it's 1, if you're dealing with a sugar, just put 1 in there. It doesn't change the math. Delta TB does the same thing. Osmotic pressure. Van Hoff factor gets put in there. finally, for Raoult's law, it is applied here. Mole fraction of a solvent equals solvent. It gets plugged in at the bottom there, because what happens is it changes the overall mole fraction. Because you get, in solution, we put the I factor, whatever it is, 2, 3, we put it down in the bottom. So we have still moles over total moles. We're going to multiply the moles of the solute by that factor. But you can see, this number being 2, 3, whatever, because of where it's placed in all these laws, it magnifies the effect. This number here is going to be, if the number is 2, double what we thought it was going to be. Same here, and actually this does the same thing. So they all have, or all exaggerate the effect of the solute when it's an ion. Again, we'll look at 2 problems when we come back from break. But when you look at the problems, keywords that are sticking out, are they saying something about volatile if we're looking at the vapor pressure problems? Are they saying strong electrolyte versus molecular solid, covalent compound? Those 2 words, this is your molecular covalent solid, these are your electrolytes. That wording will tell you whether or not you have to include Van Hoff's factor. I would, just in general, I use this form of all the equations, and then if it says it's sugar, then I make it 1. But I leave it in there so I don't risk forgetting it in another problem where it should have been there. So just a place you can keep that. You can use either equation, but I use Van Hoff's. I keep it in there just in case.
I just have a quick question. Why do we use pi as a symbol there?
It comes back from the original folks that came up with the laws. They just substituted in there, and it's stuck.
That seems confusing as
It
hell.
does. It does. But it is stuck, and nobody has ever had the gumption to say, let's just toss it out and use PV equals nRT. We're measuring the pressure. Done deal. But everywhere in the literature, they still use pi. That makes no sense to me either. I'm with you. But if I put P up there, every place you read about it, it's going to have pi for osmotic pressure. Let's take a break. Go back 5 after, 10 after. Let's take a 10 after, and we'll continue on. We have a little bit more to do in 12, and then we'll be on with 12 for talk about where we find those constants. Big thing to remember in both of these, this tells you the change in temperature, whether freezing or boiling. It does not tell you what the temperature is. You'd have to add or subtract the number to find out what the value is numerically for that. You have to know what the boiling or freezing point is, and they'll give it to you in the problem. If we look at the overall effect of this, if you have time, one of the figures that shows it pretty decent, page 574. 574, figure that's there, just shows you visually what happens, that when you have the solution, the changes that occur when you add a solvent. Just a picture worth looking at when you have time. The effect of the overall solute being there. A lot of the equations, and a lot of the problems in this chapter, the table at the top of 575 have a lot of the constants that they need. You have some common solvents, you have normal freezing points, you have KF values, you have normal boiling points, you have KV values. That table's pretty handy overall when you're doing most of the problems in this chapter. They pick out most of those materials when it comes to the actual problem that you'll do. Take a look at, we'll put up one more of them, and then we'll talk about some problems. So we had Raoult's law for the vapor pressure lowering, freezing point depression, boiling point elevation. Last one is osmotic pressure. Remember that osmosis is the flow of solvent through a semi-permeable membrane. It's a solvent that moves, not the solute. That's what defines osmosis. The solvent goes from when there's lower solute to higher solute. If you haven't seen osmosis, the definition is there. Put the words up here so we see it. T is flow of the solvent, semi-permeable membrane, and we're going from lower solute to higher. Flow, the general flow that happens in osmosis. What osmotic pressure is, though, is much different. If you have two systems, here's your semi-permeable membrane separating two areas. Solution 1, solution 2. If we have, for example, osmosis occurring, the solvent is flowing into that separate chamber. When we talk about osmotic pressure, we talk about measuring what's the force, at what rate is that solvent moving across the barrier. The only way we can measure that is if we just apply a force. We take, and we have a force pushing down on the side where the osmosis is going to. We can effectively put enough force there to stop osmosis. Osmotic pressure is that pressure. It's the force to stop osmosis. That's what we look at. You can put a piston there, you can put gases, you can, all different ways you can develop pressure. That pressure forcing down will stop the net flow of the solvent from that or into that chamber. Mathematically, osmotic pressure is symbolized with pi. It is equal to the molarity of the solution, RT.
You lowercase the m because it's the molality?
No, I put the line underneath to show you its molarity, to show you that difference. But look at this line. This really is nothing more than, molarity is moles per volume, T. If we look at it that way, this expression is nothing more than the ideal gas law, shown slightly different. From a sample. The sample of the human hormone that was collected was 0.546 grams. Finally, the KF value that we could look up. The KF value, because we're dealing with water, the water is the key. This KF value for this to that of water. When we looked it up earlier, 1.86 degrees centigrade mole. Just be careful. These problems sometimes are very short statements, but they're key phrases. They gave us the Van Hoff factor. They tell us it's aqueous. If it's aqueous, that means we're dealing with freezing point at 0. We need the KF for that. We need to find that data to bring it into the problem. Now, once we have it, it's a quick multiplication to get the delta T.